Now, there are broadly two different types of square roots out there. We have two different circles here. I'm going to give you examples of each type so you can try to figure out what the pattern might be. So on the left side, let's have square root of 9, square root of 16, square root of 36, square root of 25, square root of 1, and square root of 100. And finally, on the right side, we have square root of 10, square root 5, square root 17, square root of 99, square root 3, and square root of 2. So there's a lot more examples of this, but these are just some examples. Now, what are these? On the left, these are something called perfect squares. There's something called perfect squares, and I'm going to have you try to see if you can figure out why. On the right, in contrast, these are just simply not perfect squares. So what's so special about the ones on the left that does not apply to the ones on the right? Look carefully at the numbers to see if you can figure it out. Well, when I think perfect square, I think about squares. I think about the numbers that we can square, which is to the power of 2. So if we look at each one, we know that square root of 9 is 3, because 3 to the power of 2 is 9, square root of 16 is 4, root 36 is 6, root 25 is 5, root 1 is 1, and root 100 is 10. All of those numbers in brown, if you square them, which means if you multiply it by itself, you get the number inside the radical. So that's why those are perfect squares. Perfect squares are basically any number for which there's a different number out there that if you square that number, you get the original number. So 9 is a perfect square because 3 to the power of 2 is 9, etc., etc. In contrast, those red numbers on the right side, there's no whole number out there where if you square it, you get the number inside the radical. If you find the square roots of each of them for each and every one of those numbers, like root 10, root 17, root 5, etc., all you would find is decimals each and every time. The difference between perfect squares and not perfect squares is really important today as we build on what we learned last time regarding simplifying by breaking down the different radicals that we have. Let's jump into exactly what we're going to do today. Now, in the last video, we had some experience breaking up the different numbers inside the radical into different factors. Today, our goal is to factor out the perfect squares. What does this word factor mean? Well, a factor is basically a number where if you multiply it by another number, you get a product. For example, if we have a number like 12, we can factor 12 in a lot of different ways. For example, if we have here root 12, we can turn that into root 12 times root 1 because as we know, the numbers that are inside the radical, we can combine it, and 12 times 1 is 12. In a similar way, root 12 is equal to root 6 times root 2, because 6 times 2 is 12. And finally, root 12 is also equal to root 4 times root 3, because 4 times 3 is also 12. We can go the other way, such as root 3 times root 4, root 2 times root 6, root 1 times root 12, but we're not going to worry about the other way for now. We're just going to treat it as the exact same thing, it's just in a different order. Now, as I said earlier, our goal is to factor out the perfect squares. Which ones are the perfect squares here? Well, I really like the first one and the third one, so I'm going to box those two. The reason why I like them is because I see a root 1 and I see a root 4. I notice here that 1 and 4 are perfect squares. So as a result, I like the first one and the third one. Those are the ones, while all of these are different ones that we can factor, I like the first one and the third one the most because they have perfect squares in them. And for what it's worth, lastly, I like the third one a little bit more than I like the first one. For what it's worth, the third one's is simply more useful. Think about what root 1 is equal to and what root 4 is equal to as we try to figure out why exactly the third one is more useful than the first one is. I'll show you why in the next example in a little bit. To show you exactly why that root 1, while being a perfect square, was not as useful as the other one in the previous example, let me show you another one using root 18. How can we factor root 18? Well, we can factor it as root 18 times root 1, we can factor it as root 9 times root 2, and we can factor it as root 6 times root 3. We have these three ways of factoring. Now, between them, well, I like the first one and I like the second one. I don't like the third one as much. Why is that? Well, I know that root 1 is in the first one, and 1 is a perfect square, and root 9 is in the second one, and 9 is a perfect square as well. I don't see any perfect squares in the third one. Remember that our ultimate goal here is trying to find whole numbers. Once again, our ultimate goal in trying to find perfect squares to factor is to find whole numbers. That's going to be really important as we try to figure out exactly how to simplify. We know here that root 1 is equal to 1 and root 9 is equal to 3. The reasons might not be very apparent, but for now, just know that when we find 1 as a factor, yeah, that's cool, 1 is its own factor, but it's not very useful. 3 is a pretty useful factor because that actually breaks down what we have originally. So that's why I believe that the one with root 9 is a lot more useful than the one with root 1 in it. If that feels a little bit confusing to you, don't worry about it. For now, just try to focus on factoring so that there's a perfect square that comes out. Now, just so we're clear, there's actually multiple perfect squares that might be hidden in each number. For example, take root 72. Well, we can factor this into a lot of different ways. We can factor it as root 72 times root 1, root 36 times root 2, root 24 times root 3, root 18 times root 4, root 12 times root 6, and root 9 times root 8. I went a little fast just right now, but just know that there's multiple different ways we can factor out that number into different numbers, so that if you multiply each and every one of the two smaller numbers, we get the big number as a result. Now, which ones do I like here? Well, I like the first one, I like the second one, I like the fourth one, and finally, I like that last one, the sixth one right there. Why? Well, we've gone over this before. It's because I like the first one because there's root 1 in it. 1's a perfect square. 36 is a perfect square in the second one, so I like root 36. I like root 4 in the fourth one because 4 is a perfect square. And finally, there's a root 9 in the last one, and 9's a perfect square, which I like as well. Now, if you understood up to here, that's great. You're ahead of the game already. But just to make sure that I am covering all my bases, as this is a concept that we'll go over more later, I just want to also say that the first one is not very useful because there's a root 1 in it, and root 1 is equal to 1. That doesn't really help us very much. In contrast, the second one is the most useful because root 36 is 6, and that's really big, and that allows us to factor out a lot. If that is confusing to you, don't worry about it. We're going to do that in the next lesson. For now, as long as you know how to find perfect squares after factoring out all the different possibilities, you should be fine. Phew. I know we covered a lot today. This is a really important concept that I want to make sure we master before we move on. It's probably even the most important lesson that we have so far. So let's go over some vocab so we can wrap up this time on a really strong note. We learned about a factor today. Factor of a product is like a number that can be multiplied with another number to get that product. So if you have a number, you're breaking it down into different factors. Until now, you've also mostly worked with square roots that are whole numbers. When this happens, the number inside the radical is called a perfect square. For example, root 16 is 4, and so 16 is a perfect square because 4 to the power of 2 of 4 times 4 is equal to 16. Basically, perfect squares are numbers where if you take a square root of it, you get a whole number as a result. And those are the numbers that we really like when we simplify. Now, finally, some last questions to think about is the following. Let's say we simplified something. We're finding a factor, with a factor with a perfect square. For example, root 150 is equal to root 25 times root 6. Do you think that we can simplify root 25 times root 6 any further? Is there anything we can do to simplify maybe that root 25? Is there anything we can do that root 25 to make it even simpler? These are some questions that you should be asking yourself, but for now, let's just take some time to master what we learned today. We covered a lot, and I want you to really chew on what we just studied, because I know it's going to be a lot, and it can be kind of overwhelming. You can watch this video multiple times if you need to. The more you watch it, the better for me, because I just get more views. But overall, the more you watch it, the better for you as well, because I think it's going to be really important for you to keep watching this until you're mastering it. It's really important that you master this before you move on to the next part, which will be quite simple if this part feels pretty good. For now, make sure to like, comment, subscribe. Best of luck on your practice problems, and see you next time.